Good morning. Today we are going to talk about composite materials. And later this morning we'll focus on how we use composites for applications in wind energy. And one of the most important components in composites are the reinforcements. So we're going to review some concepts on statistics. So let me, and some of these may be you may be fairly familiar with these, but let's just go through the exercise. There is an organization in the US called the Centers for Disease Control, and this is an organization that keeps track of diseases, also biological information in the US. And they did a study, and they reported the height of males in the US 20 and older. And they reported that the height of this group of people was 69.1 plus or minus 4.15 inches, okay? And then the question is, what does this really mean? What does it really mean when somebody tells you that the height of males in the US is 69.1 inches? And then you have this variability. So what it really means is that they do a survey, and they can either ask somebody to stand against the wall and they get a ruler and they check your weight. And then they build these frequency diagrams where you have the frequency normalized by some value. And then in the horizontal axis, you have the height, in this case, in inches. So this chart goes from 58 inches all the way to 82 inches. So if you have somebody like LeBron James, he's going to be way up here, very tall guy. But then on average, you're going to have 69.1. And then we have one standard deviation about this distribution, okay? Now, the question is, did they actually measure every male in the US to get this information? And there are about 340 million people in the US. And half of those are male, so you have 170 million people who are male. And then probably 100 million of those are 20 years or older. So when the Centers for Disease Control report this value, did they actually measure every citizen? Of course not. It's going to be almost impossible, okay? But there has to be a representative number of measurements to make some sense out of these values. And that's what we call the size of the sample. The sample has to be large enough for us to get some meaningful information out of this exercise. For example, if you just take 10 people and you measure their height and you plot the results, you're going to get something that looks like this, okay? If you increase the size and you measure 30 people, you get this, but then you have these outliers here. You're going to find that you don't have very tall people in your sample. If you increase your sample, then it starts changing. And obviously, as you increase your sample, in this case, if we have 300 people, then you have a distribution that looks like this, okay? If you measure 500, 3,000, 5,000, okay? So if we plot here on the vertical axis the average value as a function of the sample size, you're going to see that for small sample sizes, you have a lot of variability, okay? And as you increase the size of your sample, you start to converge into this value, which is going to be close to the true average. Now, you can only find the true average if you measure every member of the population, okay? But that's going to be truly impossible. But nonetheless, what we have found is that as you increase the sample size, you don't have to be measuring 150 million people, but these values are going to converge fairly closely towards that value as you increase the sample size. And the same is true for the standard deviation. You have a lot of variability if your sample size is small, and then as you increase the sample size, this is going to start to collapse and reach an asymptotic value. So when we talk about precision, okay, what we really talk about is our ability to estimate the parameters of the distribution. In practice, we will never know the exact values. That's a reality. unless you measure every member of the population, you will never know the true values. The best you can do is to get estimates of the parameters of the distribution, okay? That's the best you're going to be able to do. And as you increase the sample size, we find that our estimates get closer and closer towards the true value. But the only way you're going to be able to find the true value is if you measure every member of the distribution, okay? And obviously, for practical purposes, this is going to be impossible. But as long as we are aware that whenever we calculate the parameters of the distribution, these are estimates of the parameters, then we're going to be okay. By the way, the report I showed you, they only had measured 7,900 people for that study. And that turned out to be a fairly representative value of what you find in the US. Now, the second question is, why do we use a normal distribution? Okay, is there a rule written in nature that we have to use the normal distribution? Okay? And the reason why we like to use distribution is that mathematically, these are very powerful ways to represent data, okay? Especially when you have variability in the results, we like to use distributions because mathematically those can be handled fairly well. Let me skip here. So what we found is that the normal distribution does a good job for many processes in nature, okay? It does a great job. In fact, 9 out of 10 distributions that you're going to be handling as engineers can be analyzed using the normal distribution. But there is really nothing written in nature that tells you that you really have to use the normal distribution. It actually works really well. And mathematically, it's a function that can be handled fairly easily. Now, this distribution was first described by Gauss. Okay, in fact, there's a bill that has his picture. And this distribution is characterized by two parameters. One is the mean, okay? The other one is the standard deviation. And once you know these two parameters, you can really describe the entire distribution. And it's also known as the Gaussian distribution because of Carl Friedrich Gauss, the fellow who first mathematically described it. And you can see here the shape of the distribution. Now, when we talk about distribution, there are two forms of the distribution. The first one is the so-called PDF, or probability density function. And then you have the cumulative distribution function. So every statistical distribution that we're going to be dealing with today, we have, again, the PDF and the cumulative distribution function. So in the case of the Gaussian, mathematically, the form of the PDF has this shape, where these are the two parameters. This is the standard deviation sigma, and mu is the mean value, and this is the value of the variable of the distribution. And then for the cumulative distribution function, what you do is you integrate from minus infinity up to the value of x, and then you have, again, your two parameters, the mean value and the standard deviation, okay? Now, as engineers, I'm sure you have dealt with different distribution functions, okay? And they are widely used. Engineering is probably the discipline that uses the most number of distributions. And there is one in particular that we're going to talk about today, and that's the so-called Weibull distribution. Who's familiar with the Weibull distribution? No? So Weibull was a Swedish engineer. His name was Walode Weibull. And this is one of the, especially in the area of reliability, ceramics, this is one of the most widely used distributions. And he was working for an engineering firm in Sweden when he first developed this distribution. And this is the first page of a paper that was published in the US. There's an association called ASME, the American Society of Mechanical Engineers. They have a journal, and he published that paper. This is one of the most widely referenced papers in the history of engineering. I mean, I don't know how many citations this paper has. And sometimes, you know, when we do science, we are always very concerned about publications, and we write our resume, and we like to say how many times our papers have been referred to. And then when we compare ourselves to somebody like Weibull, you know, when that paper has been cited 100 million times, we realize that we are in a very different league. So this is one of the most famous papers that you will ever find in the area of reliability. And again, as you will see, this applies fairly well to ceramic materials. Now, if you read the paper very carefully, that Weibull states that the only merit of this distribution is that this is the simplest mathematical expression that can be used to describe some observations, okay? And this is important because a lot of people have been trying to find some sort of explanation based on principles of nature. And really, the only reason why people use this distribution is that mathematically it's very simple to use. Now, as you will see here, there are some implications for this function when it comes to reliability and the behavior of the mechanical behavior of materials. But in reality, there are no physical basis for why this function should do the job other than mathematically it is very, very simple to use. And what's most important is that when you feed that function to some data, this does a very good job describing the trend of those data, okay? Now, you will always find critics. So when he first published his paper, the paper did a very good job, and I'm going to show you some examples of how he applied his function. But people said, oh, baloney, that function is meaningless because it has no theoretical basis. Well, so what? What about the normal distribution? People have tried to understand random processes with normal distributions, and they can do a very good job describing one related to the other. And this was one of the major criticisms that Weibull had received, that they said, well, your function has no theoretical basis. His point is that you could say the same about pretty much every distribution function that we use in engineering, including the normal distribution. And what's most important is that Weibull showed that he can apply his function to in biology, and he can apply to materials, as you will see. And his point is that it doesn't matter if there are no fundamental reasons for why this function can do such a good job, other than it does a good job, and mathematically we can handle it fairly well. So what is the Weibull distribution? Well, as I mentioned, whenever you talk about distributions, you talk about the PDF and the cumulative distribution function. This is the form of the PDF. In this function, there are two parameters. One, this so-called Weibull modulus, or M, okay? And this one, which is the characteristic parameter of the distribution, sigma sub 0. And M appears here, and sigma sub 0 appears here. And then if you integrate from minus infinity to x, you get this cumulative distribution function, which is 1 minus the exponential of minus x over sigma 0 to the m, okay? And we're going to be using this function this morning, and I'm going to show you what are the implications of using that function for materials. So the same way we have a mean value and a standard deviation and normal distribution, in the case of the Weibull distribution, we have the Weibull modulus, and then we have this characteristic value of the distribution. You can establish some relationship between the mean and this value and the standard deviation and this value. They are not the same, but this tells you how broad is the distribution, okay? If you have a very high value of m, the distribution is very narrow. If you have a small value of m, the distribution is very broad. And this value, sigma sub 0, is going to give you the equivalent of the mean. Where is the value of the distribution centered around what value, okay? So this is the form of the Weibull distribution. And I'm just repeating here. Weibull modulus, again, this is a measure of how broad is the distribution. And the characteristic value is, tells you the equivalent of the mean, around what value the distribution is centered. So let's plot. Let me show you some PDF forms of the Weibull distribution. So here in the vertical axis, we have frequency. In the horizontal axis, we have x. And we have the two parameters that define the distribution. M equal 2, sigma 0 equals 70. So in this case, 70 is right about here, okay? And you have a fairly small value, which means that the distribution is very broad, okay? Now, something that you should pay attention to is the fact that this distribution is not symmetric. It's actually skewed towards one side. And if you, again, see where 70 is located at, you're going to see that the weight of the distribution is actually skewed towards one side. Okay? If you compare this with the normal distribution is very nice, it's very symmetric, and it's really centered right about the mean. In this case, it's a little bit different. If you pick up a value of 5, see what happens to the distribution. It gets more narrow. Okay? And here we have kept the same value of 70. See what happens when we increase the Weibull modulus. The distribution gets actually more narrow even. Okay? If you get a value of 30, it becomes very slender. Now, remember we have the PDF, the probability distribution function. We have the cumulative distribution function. So this is the cumulative distribution function for these two values. It goes from 0 up to 200 here. And as you increase this value, the probability is going to increase. That's the cumulative value, goes from 0 to 1. And see what happens as we increase the Weibull modulus. The function becomes steeper. This becomes very steep. In the case of 30, it's very, very steep. So this gives you the probability that something will happen. So if you have a value of 70, for example, the probability is going to be very high, in this case, close to 90%. So this is how we read these distribution functions. So again, the value of m, the Weibull modulus, gives you a measure of how spread is the distribution. As m increases, the width decreases. And then in the limit, if you have a very high value of m, you have a deterministic process. Okay, the probability of something happening for one value is going to be almost close to 100%. So going back to Weibull's paper, it's actually a very good paper. If you're interested in reliability and you're going to be working with ceramics, I strongly encourage you to read Weibull's paper. It's actually very well written. It's a very nice paper. And at the time, he was working in a factory, and they were making a steel. And he was able to show that his distribution described fairly well the yield strength of the steel that this company was making. Okay? Very good job. And then he started analyzing the size distribution of fly ash. Fly ash happens when you burn coal, and then ash happens because of the combustion process. So he was looking at the distribution of particle sizes, and he found that the Weibull distribution did a beautiful job describing the distribution of sizes. And then he looked at some papers where they had published the strength of cotton fibers. And he found that the Weibull distribution did a beautiful job describing the distribution of strengths, the tensile strength of these cotton fibers. And then he was looking at the length of worms, gusanos, okay? And he found that his distribution did a beautiful job describing the size of these worms. And then in his company, they were measuring the fatigue strength of a type of a steel. And he showed that his distribution did actually a very good job describing that distribution of fatigue lives. And not only that, I showed you that the Centers for Disease Control in the US had found a distribution of height for males using a normal distribution. In fact, in his paper, he shows that if you look at the height, the stature of males in British Isles, that distribution of heights could be described with the Weibull distribution. So, this was it was beautiful, very simple distribution, mathematically very easy to track, and they could describe a lot of different phenomena in nature. Okay, nothing fundamental about Weibull distribution. There's really nothing written in nature for why this distribution should do such a good job, other than it does a very good job. Now, something that has been of a lot of interest to structural engineers is this business of the weakest link theory. And the idea of the weakest link theory is the idea of having a chain. So if you have a chain and you pull the chain in tension, where is the chain going to fail. At the weakest link, okay? So if this link is the weakest of all the links and you pull it, it's going to fail right here, okay? And what people have found is that you can use Weibel distribution to describe weakest link processes in nature. And I'm going to show you how he did that. And one of the consequences of the weakest link is that the strength of materials is going to be dependent on its volume. One of the consequences of Weibel distribution is that if you have a small object, that object is going to tend to be stronger than a bigger object. Now, the idea is that the strength of materials is controlled by flaws, by defects. So let's think about a ceramic. A ceramic that has a crack is going to be weaker than a ceramic that has no cracks, okay? And that crack can control the strength. If you remember Griffith's criterion, the fracture toughness, the size of the defect, and the strength are connected. So if you have two objects, the one that has the bigger flaw is going to be weaker. And then the bigger the object, the probability of finding a larger defect is going to increase. And this is one of the consequences of the weakest link theory, that the strength of materials is going to be dependent on the volume. And that actually comes out of Weibel's distribution, okay? And that's what we know as the weakest link theory. And this is why people doing reliability calculations depend so much on Weibel's distributions. It does a beautiful job. And in fact, in nature, and I'm going to show you here when we talk about ceramic fibers, smaller fibers are stronger than bigger fibers, okay? And it just comes very nicely out of these mathematical functions. So the nice thing about Weibel is that I show you all the applications of Weibel distribution, okay? Biology, materials, natural phenomena. And in the case of ceramics, we find that most ceramics, if you look at the strength, the tensile strength of ceramics, the Weibel modulus varies between 3 and 15. Okay, materials like silicon nitride, silicon carbide, you know, they are 10. And then if you have metals, the Weibel modulus is actually very high. And that means that you are going to have less variability whenever you test metals than when you test ceramics. And this is why we build bridges with metals and not with ceramics. You know, it's the variability that you have with metals is much less than what you have with ceramics. Okay, any questions? So this is Weibel distribution. This is one of the most important contributions when it comes to reliability theory of ceramics and many materials in general. And we're gonna return to Weibel distribution here in a minute.